The objective today is to describe what the Intel manual says about floating point exceptions. And before we get started, let me explain why you are looking at a meme on the left side of my screen here. Last time, in the last video about rounding, that is how the Intel manual deals with rounding floating point numbers, I made a joke about this whole round towards zero concept, because apparently the Intel manual is telling us that sometimes this mode is called the chop mode. So my joke was that this is nerd slang, and then I said don't be offended by me saying the word nerd. I referenced this meme and here it is. So when someone says sorry for calling you a nerd, Data says there is no need to apologize. I was not offended. So I just wanted to, because of people asking to see the meme, I thought I'd go ahead and deliver that to you. Alright, so let's get busy here. The following section provides an overview of floating point exceptions and their handling in the IA32 architecture. It just blows my mind that they call it the IA32 architecture instead of x86 architecture like I think most programmers do. Well, they go on to say for information specific to the x87 FPU and to the streaming SIMD extensions, refer to the following sections. So we're in 4.9 right now, page 105 by the way, and section 8.4 is quite a ways away. There we go. I should probably remember to do this so we have an easier time referencing things. And if you're not very familiar with the concept of exceptions, there's hardware ones and software ones. I went ahead and made a pretty short video just giving you the basics, like an Eli 5 video of exception handling. Well, the second section they refer us to look to is 11.5, and that's even further away. Okay, they begin by saying when operating on floating point operands, this architecture recognizes and detects 6 classes of exception conditions. So here's all our conditions. It says that the nomenclature of a hashtag or pound sign, number symbol, whatever you want to say, or whatever you want to call that, by doing this symbol followed by 1 or 2 letters, for example, hashtag P, the symbol is used in this manual to indicate exception conditions. It is merely a shorthand form and is not related to assembler mnemonics. And I think that's particularly important to be aware of because usually when you see that hashtag in assembly, I think that is just referring to like an exact value or specific value that the programmer wants to use. And if you remember back to some of our address lessons, that could be a good connection for you to make. However, in the context of floating points, right, not addressing, if we see any of these hashtags, they are referring to these particular exceptions. Now, I wonder if there is a mnemonic like our classic, please excuse my dear Aunt Sally. I wonder if we could make one of those out of IZDOUP in order to better memorize all the 6 classes of exceptions that exist. Extra credit if you could come up with one there and post it in the comments. Alright, so we're in a section called Note. All of the exceptions listed above, except the denormal operand exception, are defined in the IEEE Standard 754. And I'm being a little facetious here by saying our processor is still compliant because why is there this exception for, what is it, D? It's the one right here, and an easy way for remember what a denormal number is just remember it's like not a scientific notation form. We learned in the last few videos that a number that is super, super tiny could not be stored in the classic normal, I guess you could call it, floating point format, so it then becomes this denormal format, which clearly creates this exception. But I think it's the type of exception that would just keep the program going. So first question, what does the nomenclature hashtag mean? And then here we go, which exception is an exception to the exceptions? So I put in parentheses, that is an exception to the IEEE Standard. Well, the invalid operation, divide by 0, and denormal operand exceptions are pre-computation exceptions, meaning these occur before any computing is done. That means the processor detects this and creates an exception before anything happens. Or if you want to be fancy about it, you could say before any arithmetic operation occurs. So a good question there would be when are the divide by 0 and denormal exceptions triggered? Now the numeric underflow and numeric overflow and precision exceptions are post computation exceptions. And I'm a teacher, what can I say? I like tables. So here we have a nice little neat table ordering the pre versus post computation exceptions. Well, each of the 6 exception classes has a corresponding flag bit, so there's your flags, and a mask bit. So there's 6 of those as well. Now, when one or more floating point exception conditions are detected, the processor sets the appropriate flag bits, then takes one of 2 possible courses of action, depending on the settings of the corresponding mask bits. What's a mask bit? And second, what do the settings of these bits determine? So if we scroll over here, you'll see there's course 1 and course 2. So let's read. Mask bit set. This will handle the exception automatically, producing a predefined and oftentimes usable result while allowing the program execution to continue undisturbed. Reminds us of a QNAN, right? So if a mask bit is set, that means one of these, IM, ZM, OM, etc., has a number 1 to it. So my next question is, if the mask bit is set, what will happen? The answer is the program will continue to go. Now, if the mask bit is clear, this will invoke a software exception handler to handle the exception. Alright, so we are at the software level here. And this question may be Stack Overflow worthy, but I'm just saying, who decides the default for this value? Maybe a better question would be like, what is the default value? Because it says predefined. Maybe the who is Intel, maybe the who is the programmer, or the compiler. Whichever it is, I'd like to know that, and I would like to know what it is. Well, the masked default responses to exceptions have been chosen to deliver a reasonable result for each exception condition and are generally satisfactory for most floating point applications. And remember, a lot of graphic stuff is floating point stuff. Now, by masking or unmasking specific floating point exceptions, programmers can delegate responsibility for most exceptions to the processor and reserve the most severe exception conditions for software exception handlers. Now, because the exception flags are sticky, they provide a cumulative record of the exceptions that have occurred since they were last cleared. A programmer can thus mask all exceptions, run a calculation, and then inspect the exception flags to see if any exceptions were detected during the calculations. In the IA32 architecture, floating point exception flag and mask bits are implemented in 2 different locations. So there's your question, where are the exception flag and mask bits located? The first answer is in the x87 FPU. That's the status word and control word. So that's kind of tricky. That's like 2 locations in one. Well, it says that the flag bits are located at bits 0 through 5 of the x87 FPU status, and the mask bits are located at bits 0 through 5 of that same area in the control word. So if you want to be nice and specific when answering that question, you could just highlight the idea that it's bits 0 through 5. So it looks like we have 12 bits in total, which makes a lot of sense because we have 6 classes of exceptions. Now the second location is the MXCSR register. The flag bits are located at 0 through 5 again, just in this MXCSR register. And then the mask bits are located at bits 7 through 12 of this register. So I wonder what that register's total size is. Is it 12? Or I should say 13, because 0 is a number. Well, although these 2 sets of flag and mask bits perform the same function, they report on and control exceptions for different execution environments within the processor. The flag and mask bits in the x87 FPU status and control words control exception reporting and masking for computations performed in the x87 FPU instructions. Oh, I meant to say with those FPU instructions. The companion bits in the MXCSR register control exception reporting and masking for SIMD floating point computations performed with those instructions. So I thought that was a kind of cool term right there, companion bits. So having a little fun here, which register holds the companion bits to the x87 control and status word bits? Alright, well, our last 2 paragraphs. Note that when exceptions are masked, the processor may detect multiple exceptions in a single instruction, because it continues executing the instruction after performing its masked response. For example, the processor can detect a denormalized operand, perform its masked response to this exception, and then detect numeric underflow. And you should note that underflow and overflow are super similar concepts. Overflow means there's more data than we can represent, and underflow is more data than we can represent, but because it's a super tiny number. I was surprised to even find this underflow term. But I suppose if you're a programmer and you're talking with scientists who are working with really, really tiny numbers, if you were to say, oh, this creates an overflow, that might just not settle very well with them. I sure would like to interview the people who wrote this manual and ask them questions like that, like where did you come up with this term and why? Well, anyways, they end this section by saying to look at another section, the one we're about to get to, and this is called floating point exception priority, and they say to look at that for a description of the rules for exception precedence when more than one floating point exception condition is detected for an instruction. So basically what happens when you have a gigantic mess. Well, that's it for today. Next time we'll go ahead and talk about floating point exception conditions.